So this is lecture number 4. We are on PowerPoint number 2, so let's everyone please load it up. We should still have the second PDF. And let's see where we left off. Does anyone know where we left off? The last thing we did. I really should keep track, but
we were on slide 30, Professor.
For slide 30, have we done 30 yet, or we're ready for 30?
We were done with 30.
Okay, so we constructed a 5-number summary. Could someone remind me, please, what the 5 numbers are? Can you go over how to find an outlier again? And also, the person who just asked me that, I don't want to say your name. I did see an email from you that you were having a question on the homework, I believe. So why don't you stay after class for my next office hours and we can discuss that, okay? The question was, how do you find an outlier? That's what he asked. So the first thing you do is you set all your data from lowest to highest. So let's write out, hopefully you guys can see this okay, the board. Otherwise, what's the point of me buying it and installing it? So the first thing you do is you arrange your data from lowest to highest. And the minimum, right, the minimum on one side and the maximum on the other side, those are easy to find because if you have all your data from lowest to highest, the minimum is simply the lowest number and the maximum is simply the highest number. That part's easy, correct? Hopefully there's no difficulties in finding the minimum and the maximum when you list them in order. Step 2 is we find Q2, also called the what? What's another name for Q2?
Median.
The median. So we find Q2 or M, we find the median. And then, so step 1, run them in order. Step 2, the min and the max. I guess now step 3, find the median. What will be step 4?
Subtract Q3 and Q1.
You can't subtract Q3 and Q1. I don't have Q3 and Q1. So what is step 4?
All right.
Find the medians, Q1 and Q3.
Find Q1 and Q3, right? Find Q1 and Q3. Q1 is the median of the left and Q3 is the median of the right. So you have the middle guy, which is the median. Then you have the median of the left side and the median of the right side. In all 3 of those, you do the standard even or odd rule. And once you have Q1 and Q3, then you can calculate the IQR. And the IQR is Q3 minus Q1. The IQR is the distance from Q1 to Q3. Does that make sense so far?
Yes.
Okay. Next, the question is, how do you know whether something's an outlier? So what we do is we go from Q1 and we go to the left. How far to the left? 1.5 times the IQR. So whatever the IQR is, whatever the interquartile range is, we multiply it by 1.5 and you go Q1 to the left. Anything past that is an outlier. Then we do the same thing. We go Q3 and we go to the right, 1.5 times the IQR. And anything past that is an outlier. I remember where we stopped. The question was, if you do find an outlier, what happens at that point? I don't think we did the modified box plot, correct? Yes, did we talk about a modified box plot yet? I don't think we got that far, did we?
No.
No, okay, so what we have right now is a situation of data where you have the min. Yeah, I saw. You have the min, you have the max, you have Q2, you have Q1, you have Q3. We calculate the IQR. You do 1.5 times the IQR. You go to the left of Q1 and the right of Q3, and anything beyond those 2 points is an outlier. Or at least it's a suspected outlier. We can't say definitively that it's an outlier. It's a suspected outlier. What do you do with a suspected outlier? If you have a suspected outlier, you have to analyze. You have to actually look at the situation and decide, is this a mistake? Is it not a mistake? Is it truly an outlier? Is it not an outlier? That's really more of a non-statistical practice or procedure, is determining whether or not something truly is an outlier. That's more common sense and logic than it is doing the math. All we can do here is talk about whether it's a suspected outlier. So to illustrate what happens in that situation, let's go down. Let's go back up a few slides. Let me find it. Hold on. Okay, so on slide 30, we have 15 points, correct? I think it's 15 points. 20 points. 20? 1, 2, 3, 4, 5. Yeah, we have 20 data points, correct? If you look, yeah, go ahead. Someone has a quick question.
My question was, so the 1.5 times IQR plus Q3 would give you the suspected max?
Yes,
And
no. Q3 plus 1.5 times IQR gives us the border for which anything past that would be considered a possible outlier.
And then for the Q1, it would be
Q1 minus 1.5 IQR is the same thing. Anything past that is a suspected outlier. So then you look at your data and you ask yourself, okay, go ahead. You ask yourself whether or not we have any data that falls past here or past there. And if you do, they are suspected outliers. And if you don't, then they're not suspected outliers. In this example of question 30, the question, not question 30, but slide 30, the question is, do we have any suspected outliers in this situation? So let's look at what we have. First, what is the min? On slide 30, it literally says it. So this shouldn't be too tough of a question, 5. And what's Q1?
15.
15. And what's the median?
22.5.
And what's Q3?
42.5.
And what's the maximum?
85.
All right, they're all listed for us, correct? Okay,
Yeah.
So now let's find the IQR. What's the IQR? Remember, the IQR is Q3 minus Q1.
27.5.
Huh?
27.5.
27.5, correct? So then we take the IQR and multiply it by 1.5. What do we get when we take the IQR and multiply it by 1.5? And by the way, the number 1.5, you can't ask where that came from. Somebody a lot smarter than me and you decided that 1.5 was the right formula. And why 1.5? Why not 1.48 or something else? I have no idea. It's just the general rule is that multiply it by 1.5. So the IQR times 1.5 is 41.25, correct?
Yeah.
Okay. So now what we do is we do Q1 minus 41.25. You do Q1 minus this number. If I take Q1, which we know is 15, and I subtract 41.25, what do we get?
Negative 26.25.
Yeah, negative something, right? Do we have any data past that number to the left?
No.
No. So there's no suspected outliers on the left side. So now let's go to the right side. Okay, take the same number and do Q3 plus that number. What do we get when we do Q3 plus that number?
83.75.
83.75. Do we have any data past 83.75?
Yeah.
Yes. In fact, we have one data point. So that data point would then be a suspected outlier, would it not?
Yeah.
That's the rule. Anything past that point, past the border on either side is then a suspected outlier. So what do we do when we have a suspected outlier? We do the following. We modify our box plot. A modified box plot is almost the same as the original box plot, with one difference. You know how normally for a box plot, the lines on the side go to the min and go to the max? Right? For the regular box plot, it goes to the min and max, correct?
Yes.
Okay. For the modified box plot, you do not go to the min and max. You go to the last non-outlier on both sides. So in our example, 85 was the maximum, correct? So in our original box plot, the line on the right would go all the way to 85. For the modified box plot, we stop at the last non-outlier. What's the last non-outlier?
70.
83.75?
No.
In the number set, you mean?
65.
In our data, what's the last non-outlier? 65, right?
65.
Right? If you look at our data, the last one before 85 is 65, right? So
Yeah.
in our modified box plot, we would stop at 65, and then we would just put a little star by 85. That's the only difference. A modified box plot, the only difference between the regular, and we'll see a picture in a second, the only difference between a modified box plot and the actual box plot is that with the actual box plot, you go all the way to the max and min. For the modified box plot, you stop. You never go past the borders of suspected outliers. So you stop at the last non-outlier, and you put stars at the outliers. So let's look a couple slides down, and we'll see this in action. Let's look at slide number 32. And you can see on slide number 32 exactly what I'm talking about. If you look at slide number 32, the the modified box plot is shown. You can see there that the New York box plot has an outlier. It is a little star on the far right at 85, correct? But it stops at 65. It does not go all the way to 85 like the other box plot does. The North Carolina box plot, by the way, the one beneath it, is that a regular box plot or is that a modified box plot?
Regular.
It's regular. There's no outliers. So I know exactly what my final value is, my max and my min are for North Carolina. And of course, I know the same thing for New York. One's a modified box plot and one's a regular box plot. So looking at those two pictures, is there any confusion on how to construct a box plot and how to modify it in the case of outliers? So this seems relatively straightforward. And if you go, well, let's answer a couple of questions before we move on. So let's look at slide 33. Again, let's try not to scroll too much. So if we look at slide 33, question, blank is the distance between the first and third quartiles. A, the mean. Oh, don't answer yet. Oh, yeah, that's right. It's private. You can answer whenever you want. Okay. So A, the mean, B, the IQR, C, the range, and D, the box plot. So what is the difference between the first and third quartiles? I'm hoping, beyond hope, that nobody gets this wrong. That would be wonderful. And I see, oh, and by the way, just so you know, I have a record not only of I'm recording the data, but I have a record of who answers questions when I ask. So I kind of use that as a means of determining after class. I usually do it on the weekends when I have a few minutes free, of seeing who answers and who does not answer as a mean of checking attendance and who is actually here and who's not. Just be aware of that. So if you don't know the answer, don't leave it blank, because leaving it blank makes me think that you're not here. Just say, I don't know, or say not sure.
So Professor, if we're here and we're paying attention and we don't write the answer, you're gonna mark us absent?
I'm not gonna mark you absent, but if I see a pattern forming,
Okay.
where lots and lots of questions go with you not saying anything.
Okay.
I know you're on video, which is great, but not everyone's on video.
Yeah.
Well, the ones who are not on video, I don't know if you're really there or not. I have to come up with means of checking, if you understand what I'm saying.
Okay.
Okay. But yes, everyone who answered said the correct answer was B, which is fantastic. That's about as easy as it gets. You'll never see something like that in the test. So don't even ask for it. Okay, next question on slide 35. It says, The 5-number summary for a set of data is 0, 20, 25, 50, and 110. Remember the 5 numbers: min, Q1, median, Q3, max. Using the 1.5 times the IQR rule, does the data set contain one or possibly even more than one outliers? Now, don't just answer immediately, because this one actually requires at least a little calculation. But the question is A, yes, B, no, or C, it's impossible to say. And of course, you're more than welcome to answer, I don't know. I'm not sure. Can you explain this again? I'm okay with that. But I'm waiting for the, again, take your time. You know, do whatever calculations are necessary. This is not a race. I'll do it myself. Got it. And just so you know, when you, okay, I have a not sure, which is fantastic. Can I repeat the question? Well, are you following along with the PowerPoint? Because I'm just reading the question off the PowerPoint. So I'm not sure, explain. I'm totally okay with that. I love it. Not sure, fantastic. Okay, those who did answer all said, okay, you're looking at the PowerPoint, wonderful. So we're on question 30, slide 35, okay. Most people got it correct, but there were a number of people who said, I'm not sure. And some I don't knows. And can you explain again, which is essentially the same thing, but the answer is in fact A. So let's understand why. Well, if I want to use the 1.5 times the IQR rule, then I first should calculate the IQR. Using my 5-number summary, what is the IQR in this example?
50 minus 20.
50 minus 20, which is?
30.
30, right? The IQR is 30. So the 1.5 times the IQR rule, what's 1.5 times the IQR?
45.
45. Okay, so now what we're going to do is we're going to go to Q1 and we're going to go 45 to the left. What's Q1?
Sorry, I have a question.
Yes, go ahead.
Is Q1 20 because the smallest, or
Q1's 20 because the 5-number summary lists the 5 numbers: min, Q1, Q2, Q3, and max.
right? So we don't have to add 20 and 0 and then divide it by 2, since.
No. 0 is the min and 20 is the Q1. That's the 5-number summary. The 5-number summary is those 5 numbers.
Okay, thank you.
Min, Q1, Q2, Q3, and max. So, so we go to Q1, which is 20, and we subtract 45. What do we get?
Negative 25?
Negative 25. And anything to the left of negative 25 is a suspected outlier. Do we have any data to the left of negative 25?
No.
No, because they told us the minimum was 0. Okay, so now go to Q3 and go 45 to the right. What's Q3?
50.
50. And if we go 45 to the right, where do we end up?
95.
95. Do we have any data to the right of 95?
Yeah,
Yes.
110.
Yeah, we have 110 because the maximum is 110. So 110 is a suspected outlier. Could we have more than one? Sure, we don't know. Maybe we have 107 in there too. They didn't tell us. But we have at least one, and that was the question. Is there one or more suspected outlier by the 1.5 times the IQR rule? The answer is yes, because there's at least one data point past that boundary. Does that make sense? Is there anyone still having a question on that one? Okay, a lack of questions leads me to say or hope that the answer is yes. Or no, nobody has.
I got a question.
Yes, go ahead.
Why is it we're counting 0 as a data set?
Because it's the min. It's the smallest value.
Right, but I mean, wouldn't all numbers start like that?
Why? Maybe you're measuring heights. Would you ever have a 0 height?
No.
So if I was measuring heights, the smallest number might be, 3 feet 6 or something like that. Right?
Okay.
This is your actual data for whatever experiment you're doing, right? Your numbers are measuring, you know, whatever they are. If I'm measuring, you know, how much water's in a bathtub, some of it might be 0 if it's not full at all, right?
Mm-hmm.
But if I'm measuring, you know, heights of people, that can't be 0. Maybe I'm measuring temperatures. If I was measuring temperatures, it can even be negative, right? So the data is the actual data, but depending on the experiment, then, you know, I have no idea what the numbers are going to be.
Mm-hmm.
So now someone said, is it possible to find an outlier just by looking at the prompt? For example, if there's a list of numbers and the numbers range from 20 to 50, and a number that's way out there at the end, like 100, can we assume that that's an outlier? Well, yes, you can, but why not use a very precise method when you have situations where it's not so obvious? Right? So yeah, sometimes it'll be obvious. You're right. You know, 20 to 50 and then 100. Yeah, that's obviously an outlier because the IQR is at most 30, which means 1.5 times the IQR is at most 45, which means 100 has to be an outlier. But you have a mathematically precise method, why not use it? So now we look at slide number 37, which is the box plot, which I've already mentioned. And they've actually, a few slides ago before the question, they actually drew the box plot, but I guess, interestingly enough, we haven't actually defined what a box plot is. So using the data in the previous example, I'm going to construct a box plot. And maybe, well, we had a slide where you can see the difference, but let's actually do it for our example. So for our example, the smallest value was 0 and the maximum was 85, correct? If I remember correctly, 0 to 85. So I'm going to make a number line, or at least a portion of a number line, starting at 0, 10, 20, 30, 40, 50, 60, 70, 80, to 90. Okay, I don't have to go any further than 90 because if I go to 90, then it covers all my data. So what I'm going to do is as follows. I'm going to make a dot at the minimum. The minimum was 0, correct?
Are you talking about the question we just answered?
You know what? I shouldn't.
The max is 110.
You're right. You're right. It's no. It's my apologies. I'm going back to slide 30.
Oh, okay.
So it wasn't 0. Thank you. Slide 30. The minimum was 5. So I make a dot at 5. What was Q1? It was 15. So I make a vertical line of 15, and I have a line from the minimum, which is a dot, to 15, vertical line. And then 22.5, another vertical line. I make a box. It's called a box plot. And then 42.5, another vertical line, another box, the box plot. And then the maximum was 85, so a dot. And that is my box plot. The box plot is nothing more than 2 boxes and 2 dots with lines. And if you go to slide number 32, you can see that my New York box plot looks something like that, does it not? Well, that's a modified box plot technically on page slide 32. Because remember what we do if we have an outlier, we stop at the first or the last non-outlier, and then we make a little star. So the first one is the box plot, and the second one is the modified box plot. Do those make sense?
Yeah.
For this particular example. So if you look at slide 37, how to make a box plot. It says the 5-number summary divides the distribution roughly into quarters. Line, first box, second box, last line, quarters. This leads to a new way to display the quantitative data called the box plot. A central box spans the quartiles Q1 and Q3. A line in the box marks the median M. And lines extend from the box out to the smallest and largest observations. Very self-explanatory, right? The picture basically is just what they just described. Does that make sense? Yeah? Are there any questions on that? Makes sense, right?
Yes.
So if you go to the next one, the next slide, again, we have two box plots, one on top of the other, New York and North Carolina, with whose data is below. They both have the same minimum. They have different quartile ones, they have different medians, they have different quartile threes, they have different maximums. And notice that based upon our 1.5 times the IQR rule, not only do they have different maximums, but one maximum is an outlier, in particular for New York. In the next slide, they do exactly the same thing. This time they do regular box plots. There's not a modified box plot here, and these ones are vertical. It's the same situation, but this time we have vertical box plots instead of horizontal box plots. Make sense? Okay, nothing really there. So let's look at the next question. Wait, don't scroll yet. Don't go to the slide. Because whoever made this is horrible. They put the answer on the slide. So make sure you scroll slowly until you have the A, B, C, D and not past it, because the answer is right afterwards. Some idiot put the answer right there. And the question is, what is the approximate interquartile range, or the IQR, of male wrist girths, which is the circumference of a male wrist? Based upon the, I think it's circumference, maybe it's diameter, I don't know. Probably circumference with those numbers. So look at the data and the box plots on the left, on the right, and then answer the question. Is it A, 2.5, B, 1.5, C, is it 1, or D, is it 3? Go ahead. So I'm getting lots of, oh, someone asked a question. If you have multiple data points that are, yes, if you have multiple data points that are outliers, you'd have multiple stars in the modified box plot. That's correct. So it looks like most people said B. I did see a C there, which is 1. But I guess if we are being a little accurate here, Q3 is roughly what number?
18.
18, a little less than 18 looks like it, right? Maybe 17.9, but about 18. And Q, you okay there?
Yeah.
Sounds like something fell. All right, and Q1 is what?
16.5.
16 and a half roughly, so 18 minus 16 and a half is about 1.5. I think that's the most accurate one. So yeah, 16.5. Accidentally saw the answer. Yeah, you can't do much about that. Okay, so let's skip the next slide, which is the same thing. And we had the question on slide 42, which is a different question. It says, what is the approximate range of a male, the approximate range, not the interquartile range, which was what we did in the last example, but the approximate range of male wrist girths. So think about that and send me your answer. So we still have got it correct if we got 1 on the previous one. I mean, it seemed to be between 1 and 1.5, but I think 1.5 was I mean, if you had to pick, I think 1.5 would have been more accurate. We have a not sure on this one. So remember what the range is. The range is just maximum minus minimum. The range is just maximum minus the minimum. So the maximum value looks to be what?
19.5.
About 19.5. And the minimum looks to be about what?
14.5.
14.5. And therefore the range would be A5, which everyone who answered got. Someone did say wasn't sure, but hopefully you are now. Oh, then A, he says. Yes. Wait, I'm kidding, not C. Well, it's a good joke. And you had me going there for a minute. Okay, so then we have the answer. So now let's look at slide 44, which is an extremely important slide because it connects the box plot to the distribution. And the basic rule of thumb is as follows. Remember the box plot divided into 4 parts, the line, the first box, the second box, and a line. If the length of the line is long, the distribution is low. And if the length of the box is short, the distribution is high. So let's look at the first, the box plot A, or I guess they label it as B. A is in the middle. So let's start with the middle then. I changed my mind. If we look at the one in the middle, we have what's called a bell-shaped distribution. Looks like a bell. And what we see is the 2 boxes are shorter than the 2 lines, correct? Which means the graph is going to be higher at the location of the boxes than the lines, which is why the graph is high in the middle and then it tapers off to the side because it drops. Does that make sense? If we look at B on the top left, we have a very small box on the right, so that means the graph is highest there. And then what we have is that the box to the left and the line to the right are roughly the same size, which means the graph drops and is medium-ish there. And on the left, we have a long tail, which means it really drops even more, and we have a long left skewed distribution. C is very similar, but it's the other way. It's a right skewed distribution. I have a question here. On the box plot on your whiteboard, top one will be skewed to the right. Yes, 100% the top one is skewed to the right. Exactly. If we look at D, we see that all 4 pieces have roughly the same length. And therefore, the distribution is roughly the same height, or exactly the same height everywhere. We have a uniform distribution, or a rectangular shaped distribution. And then on the left, we have what's called a U-shaped distribution. We have big boxes and small tails, or small lines, which means it's short by the boxes and it's high by the tails. Now, in real life, you might come across scenarios where different distributions are appropriate. The one in the middle is arguably the most important distribution. It's called the bell curve. It's called a normal distribution or a Gaussian, if you've ever heard any of those terms. Why is the Gaussian important? Because most natural phenomenon are measured or have a distribution that is bell curved. Think about height, for example. The average height is 5'8", 5'9", whatever it is, and the majority of people are somewhere near there. And as you get really tall or really short, the proportion of people who have that feature drop off, right? And you have a bell-shaped distribution. What's an example of a U-shaped distribution? Something that if the value is low, there's lots of occurrences. If the value is high, there's lots of occurrences. And if the value is in the medium, there's not so many occurrences. Someone actually came up with a really great example last night when I was teaching my class. But I'm wondering if any of you can think of a situation where low numbers give you high frequencies, high numbers give you high frequencies, but middle numbers give you low frequencies. Someone really came up with a great example. Well, let's see if any of you guys could do something that's the same. Nobody? Listen, it could be wrong. Don't worry about that. Just, you know, shout out something.
Repeat the prompt.
I want to come up with a distribution that is U-shaped. That means low numbers and high numbers should have high frequencies and medium numbers should have low frequencies. We want it low in the middle and high on the top and the left and right. Can we think of something that would have a distribution that looked like that?
A skateboard ramp.
Well, again, I'm not looking for a physical object that looks like that. I'm looking for a distribution. Okay, this is not a physical object. I mean, it does look like a skateboard ramp, it's true, but I'm looking for a distribution. Products based on price, based with income. That sounds very confusing. I hope you understand.
Maybe
Someone else said test grades, right? Test grades is actually a great example. You know, I taught physics for years. I still teach physics. And in physics, you have those who get it and do very well, and those who don't get it and do very poorly. And you really don't have that many grades in the middle. Either you get it or you don't. So yeah, that's actually a great example. Diseases could be one. Someone says, what do you mean by that? Diseases could be one. Since young kids get them frequently. Okay, so young kids get diseases frequently. Older people will get them frequently also, but middle-aged people do not. I don't know if the data supports it or not. It might. I don't know. It could be right, but I don't know enough about that kind of thing to know. Someone said sleep. Babies get a lot of sleep, right? They get like 12 hours a night, right?
Like kids have like a lot of time, and middle-aged people they don't have a lot of time because they're working.
Oh, shit.
Alex, sorry about that.
Shit, man, that's cool. It's all right.
My bad, big dog.
It's all right, dog. It's all good.
So I was talking. I meant kids have a lot of time when they're young, but when they're aged and working, they have little time. But when they're old, that's when they have like a lot of time again.
So what exactly are we measuring here? Because remember, it's not how much time they have, it's how often something occurs.
Professor, what about like the sale of diapers? Since like babies wear a lot of diapers and old people wear diapers too.
Okay. So diaper sales as a function of age.
Yeah.
Young people, lots of diaper sales. Old people, let's not talk about that. I'm a lot closer than all of you guys are, but old people, lots of diaper sales. And medium-aged people, not so much. That's a pretty good example. Some of these are very good. I'm not going to go through all of them. The one that someone said yesterday, which I really liked, was car crashes or car accidents. When people first get their license, they tend to be a little reckless. They tend to get, young people get into car accidents significantly more than middle-aged people who now own their own car and are more careful, some more experience. And then you get older, and of course, reflexes drop. Wasn't that in our class on Tuesday? I remember someone saying that. You know what? I teach so many classes, I don't even forget. I hope we didn't talk about this last time. If we did, we did, and I apologize. Maybe it was. I don't know. I thought it was yesterday, but I could be wrong. I'm teaching 8 classes this semester, and I'm taking a class of my own. And I'm interning somewhere. So I kind of get tired a lot, and sometimes a little, I forget what's from what. So if that was our class, I apologize. But anyways, that's an example of a U-shaped distribution. Let's look at the next example on next question on slide 45. It says the shape of the box plot below. This is a vertical box plot. What class are you taking? I'm taking Chemistry 102. I have a master's degree in math. I have a master's degree in physics, and I decided I would like to get a degree in chemistry. So every semester, I take a class in chemistry. And this semester is Chemistry 102. So I could take organic chemistry next semester, hopefully. Why would you torture yourself? That's a good question. Why would I torture myself? It's a great question. I guess I kind of like this stuff. So chem is fun. I appreciate that. Anyway, so this question, the shape of the box plot below can best be described as A, bimodal, B, left skewed, C, right skewed, D, symmetric, or E, uniform. So let's say our answers. What do we think this one is? I had a C, but then, wait, no, it's B. I have some of B's. I have some more C's. So I have mostly B's, which is the correct answer. Not so many C's, but C's I do have a lot of. So remember, a left skewed distribution means the tail is on the left, which means the long line's on the left. And a right skewed distribution, the long line's on the right. In this case, if I take my box plot and I turn it, I see the lines on the left. Now you might say, well, just turn it the other way. Well, no, because look at the numbers. The bottom of the box plot is 0, and the top of the box plot is 15. So if you're going to label it, lay it on its side, it has to be with the 0 on the left and the 15 on the right, and therefore the tail's on the left, and it is left skewed. Does that make sense? Do we have any questions on that? Seems good? Okay. So someone did have a question, makes sense. Camera's reversed, so it looks like you're turning the tail to the right, by the way. My camera's reversed. What do you mean by that?
It's probably inverse.
Yeah, but you're looking at the same you're looking at the same box plot that I am on the PDF, right?
Yeah.
So you're not looking at my box plot, you're looking at your own box plot. And with your own box plot, you can only turn it, the 0 has to be on the left and the 15 has to be on the right. Correct? Does that make sense? So even if mine is backwards or something, on your own, the way you turn it, the 0's on the left, the 15's on the right, and therefore, hopefully, at this point, we all agree that it's left, even though if there was some confusion with orientation. So let's go now to slide 47. And slide 47 says the 5-number summary for a set of data is 0, 20, 25, 50, and 110. We've used this data before to determine if there were any outliers. This question's a little different. Is the distribution skewed to the right? A, no, B, yes, or C, it's impossible to say. My recommendation for this one, if you don't see it, is to make the box plot if you haven't already done so. And from the, if you look at the box plot, you should be able to use the rule that we just said, which is the skewness comes from the long line. So is the distribution skewed to the right? Is it skewed to the left? Is it not skewed? Is it impossible to say?
I have a question.
Yes, go ahead.
So if you're looking at the data, like the set of numbers,
yeah,
see that one is like way out, do you still have to draw it out?
Well, again, someone asked something like this earlier. If it's obvious, I get that, right? If it's really obvious, you can just tell by looking at the numbers, that's fine. But if you're unsure or it's not so obvious, I'd recommend writing it out or drawing it.
All right.
Does that make sense?
Yes.
So in this case, we can see that the first tail, the line from 0 to 20 is length 20. The first box is length 5. The second box is length 25, and the right tail has length 60. So because the right tail is 60, it's got a long tail on the right side, and a long tail on the right side means it's skewed to the right. So the answer is yes, B, it is skewed to the right. Okay, let's look at the question on page 49. Question on 49 says, look at the following side-by-side box plots and compare male, female, and male shoulder girths. I guess that's, again, the circumference at your shoulders. Based upon the female, which is on the left, and the male, which is on the right, box plots, would you conclude A, females have a typically smaller shoulder girth than males, B, females have a typically larger shoulder girth than males, or C, females and males have about the same shoulder girths? A, B, or C? So I'm looking down. Of course, I don't know where the last question ended and this question began. I guess I could look at the timestamps. but it was pretty close to the last one. So it looks like at 4:49 p.m., everyone answered A. And the last B was at 4:48, which was a slew of B's, which I think was the last problem. So it looks like everyone got it right. The answer is A. So let's now go to slide 51. Looking at the following box plots, we want to compare female and male thigh girths. Females have a typically smaller thigh girth than males. Females have a typically larger thigh girth than males, or females and males have about the same thigh girth. So let's do that one. So everyone seems to be able to interpret side-by-side box plots fairly well because everyone got the right answer. Well, not everyone. Sorry, I spoke too soon. Most people did say B, but I did see, sorry, C, but I did see a B in there. A B says females have a typically larger thigh girth than males. And maybe you're saying that because the top of the female box plot is a little bit beyond the top of the male box plot. But the typical one would be a measure of center. And their centers seem to be roughly right around the same. Right? And even the top and bottom are not that far off each other. Would you agree with that? So I would say C, and the answer is in fact C. Let's look now at slide 53. Which group has the largest spread? Now, remember what spread is. Spread is another term for variability. And unfortunately, variability is a little vague in its terminology. Doesn't mean the range, doesn't mean the interquartile range, doesn't mean something else which we haven't learned yet. The range is a little tough. Yeah, I would think of it as the range. So be very careful here before you send your answers because the order of A, B, C, D is not the same order as listed in the actual box plot, left to right. It's backwards, I think. So let's do this one, which is which group has the largest spread? Now, in this particular example, let's answer it in two different ways. And let's do it verbally because, you know, I'm going to ask two different questions. If by spread we mean the actual range, then which group has the largest spread?
Single males.
Single males.
Single males.
Single males. If, on the other hand, we mean the interquartile range, the IQR, then which group has the largest spread?
Hey, Andrew, I'm taking your earphones.
I'm sorry?
Single males as well.
Well, I don't know.
Both single males and females.
Mary?
I don't know. I see 3 of the 4 being about equal in that regard. Right? The first box plot, the third and the fourth, their IQRs kind of look the same, don't they? I mean, the second one is significantly smaller. There's no question about that. But the first, the third, and the fourth are really comparable. So they probably meant the range. So if you look at the answer, we do get D. So that must have been what they mean because it really doesn't make sense otherwise. Otherwise, there's 3 different answers. But do you agree that they kind of look the same, the other 3? I don't really see one as, I mean, one's lower than the other, but in terms of its variability, which is how wide it is, it kind of looks the same to me. So, you know, the second one, certainly small, but the other ones, okay. All right, now slide 55. Now we have something else entirely. We're going to put box plots and 5-number summaries and interquartile ranges and all that stuff to the side for a bit because we're going to learn a completely different method of computing a measure of variability. And this method is mathematically more complicated, but luckily you're going to have a calculator that does it for you. Or have a calculator that does it for you because to do this by hand will be really, really annoying. The method is called the standard deviation. And it is the most common measure of spread. Okay, the IQR is nice, not questioning that. But the standard deviation is the most common measure of spread. And what it does essentially is it measures how far each data point is from the mean. And this is the first thing that you must know or memorize or understand. Never use the standard deviation with the median. Standard deviation is used whenever you're going to use the mean. The mean and the standard deviation go together. The median and the IQR go together. If you're going to use the median, use the IQR, which needs the median. If you're going to use the mean, then use the standard deviation, which requires the mean. In other words, each measure of variability, the IQR and the standard deviation, require either the mean or the median to calculate. So whichever one it requires, use it with that one. So if I ever say, do we want to use the mean and the IQR, the answer is no, never. And we never use the median and the standard deviation, ever, because they just don't go together, okay? But of course, that still leaves us the question for how to calculate the standard deviation. And we do so by first calculating the variance, which is very similar or connected to the standard deviation. Here's what we do. Step one, you have all your data points. Now, if I was going to get the IQR, what would I do first? Let's recap. If I was going to get the IQR and I have all my data points, what's the first thing I would do?
Subtract Q3 minus
Oh, I
Q1.
said first thing.
Oh,
You don't even have
sorry.
Q1 yet. What's the first thing you do?
I thought you said you had all your.
No, all I have
Sorry,
is my
never
data
mind.
points. It's okay. I got my data points. What's the first thing I do? Yes.
Range.
Well, you don't want to list them out of order, someone said. Oh, I'm sorry. List them out in order. Yes. List them out in order. I saw out. I thought it was out of order. List them in order. Calculate the median, the left median, the right median, Q3 minus Q1. You have the IQR. Right? That's the way we do it before. To calculate the standard deviation and the variance, we do a completely different method. What we do here is as follows. The first thing we do is we find the mean. How do we find the mean? We add all the data points up and divide by how many we have, right? We did that in the beginning of this chapter, correct? The mean is the sum of the data points divided by how many data points we have. That's how to find the mean. That's step one. Then we take each individual data point and subtract the mean. So we do the first data point minus the mean, the second data point minus the mean, the third data point minus the mean. We go through every one of our data points and we do each one minus the mean. These things are called the deviations. Okay? How far it deviates from the mean. These are the deviations. So if my first data point is 10 and the mean was 5, my deviation will be 10 minus 5, will be 5. So we calculate all of the deviations, x1 minus x bar, x2 minus x bar, x3 minus x bar, all the way through the last one minus x bar. Make sense? Then we take all those numbers and we square each of them. So we square each deviation. Why do we square them? Because if I didn't square them, I would get nonsense as this approach, because some of them are positive and some of them are negative, and they would add to 0. The reason I square them is to make everything positive. If everything is positive, then I don't get 0 when I add them. So again, to recap, step 1, calculate the mean. Step 2, calculate all your deviations. Step 3, square all your deviations. Step 4, add them all together. So if you look at the formula on slide 55, at this point, we have the numerator of that big fraction. We have x1 minus x bar squared, not times 2, that should be squared. We have x2 minus x bar squared, and we have all the way through xn minus x bar squared, all added together. So let's see, x bar, deviations, square the deviations, add the deviations. Step 5, divide by n minus 1. We don't divide by how many data points there are. We divide by one fewer than that. If I have 100 data points, I divide by 99, not by 100. You divide by 100. Sorry, 99 I meant. I'm sorry. We don't divide by 100. We divide by one less than that. We divide by 99. Okay. So at this point, we have found the mean. We have found all the deviations. We have squared all the deviations. We have added all the deviations. And then we have divided by n minus 1. What you have at this point is called the variance. And it's labeled by s squared. The variance s squared is what you have by this process. If you want the standard deviation, which we do, you just take the square root. So last step, take the square root. So again, to recap, the mean, each deviation, square the deviations, add the deviations, divide by n minus 1, and finally, step 6, you take the square root. That gives you the standard deviation. Who would want to do a problem by hand like this? Nobody's sane. So luckily, we have our nice calculators, hopefully, and those calculators can do it all for us so that we don't have to, because it's really a pain in the derriere or derriere. I don't even know how to pronounce it. Anyone know? Is it derriere or the derriere? N is the, I have a text here. The question is N the population? Not technically, N's a letter. N stands for how many elements there are in the population. So derriere, oh, derriere. Oh, how French sounding that is. Okay, so it's the derriere. All right, so let's look at the next slide, calculating the standard deviation. Let's do an actual example. Consider the following data on the SAT critical reading scores for 5 Georgia Southern University freshmen in 2010. 1, calculate the mean. How do we calculate the mean? Well, you add up the 5 data points. What are the 5 data points? Well, luckily they gave us the 5 data points, 650, 490, 580, 450, and 570. I know them exactly because they're in the table. I don't have to look at the dot plot on top. The dots represent the data points because that's only an approximation. I have a table and I know it exactly from the table. Okay, does that make sense? So 1, calculate the mean. How do I do that? I add them all up and I divide by 5. Based upon what you see to the right, without actually doing it yourself and assuming that they did it correctly, what is the mean?
548.
548.
548. Jamar, yes, the 2 is supposed to be an exponent. So the answer, 548. So the mean is 548. We'll just assume that they did it correctly because they can't make that many mistakes, right? Question 2, calculate each deviation. The deviations are the data points minus the mean. So 650 minus 548, and 490 minus 548, and 580 minus 448, and 450 minus 548, and 570 minus 548. And we have our 5 deviations. So based upon the table to the right, assuming they did the math correctly, and I'll give them the benefit of the doubt, what are the 5 deviations?
102.
102.
Minus 58.
Technically negative 58, but I hear what you're saying. Next.
32.
32.
Negative 98.
Negative 98.
22.
And 22. Now, if I were to add those 5 numbers, what do I get?
Yeah.
0. That's correct. The sum of the deviations is always 0. Always. So I'm not going to add them. What am I going to add? I'm going to add what I get when I square them. Step 3, right? First, find the mean. Step 2, find the deviations. Step 3, square them. So the third column, 102 squared, negative 58 squared, 32 squared, negative 98 squared, and 22 squared give us 5 numbers. Now, when I add up those 5 numbers, I will not get 0 because they're not negatives, right? They're all positives. How can you get 0 when you add up 5 positive numbers? You can't. So you get something. Let's do it quickly on my calculator. I get 10,404 plus 3,364 plus 1,024 plus 9604 plus 484, I get 24,000. Oh, wow, someone beat me to it. 24,880. Sorry, I wasn't looking. So now that we've summed up the squares of all of the deviations, what do we do next?
I have a quick question.
Yes.
Prior to squaring each deviation,
Yeah.
you mentioned that if you add all of them up, the sum of the deviations are going to be 0.
Yes.
Is that a rule?
That's a universal rule. The sum of the deviations is always 0.
Okay. Thank you.
You can prove it, and if I was so inclined to do it, it's not a hard proof, but it doesn't illuminate anything. So I'm not going to take the time. Okay, so we added up the 5 squares and we get 24,880. And the question is, what do I do next in my pursuit? I get the variance. Okay, great. Divide. Divide, someone says. Fantastic. But give me more specifics. How do I get the variance? What do I divide by? Oh, someone said divide by 4. Okay, so divide by 4 because there's 5 data points and we divide by 1 less than the number of data points. So we divide by 4. What do we get?
6,220.
6,220, so that is the variance. 6,220 is the variance. But I want the standard deviation. So, huh? You square root it, exactly. Not the square, someone forget the square, get the square roots. Squaring is multiplying by itself. Square rooting is asking what would I multiply by itself to get this. Square roots usually get smaller, squares get bigger. So someone said to me 78.87. And that is approximately what I get. So the square, how do we get the 6,000 number? We added up the squares of the deviations. So we added up the 5 numbers in the last column. I'm still a little confused. What is n? N is the number of data points. We have 5 data points here.
What was the final number that you?
78.87.
Oh, okay.
N is the number of data points. If you look at the table, there's 5 data points. Or look at the dot plot, there's 5 data points. That's N, the number of data points. X1, X2, X3, X4, X5. Yes, no, maybe so? When someone asks the question and I answer it, I need a follow-up response to my response, so I know that whether or not you get it or not. So otherwise, I can't see your face, so I can't see whether I can. Oh, I get it now. Well, you're getting it. But someone asked the question. Someone else asked the question. So I'm just waiting for him to say something, and he's not doing it. So I will just go on then because I don't have anything to go on. If you look at the next slide, they finished it for us. They were so sweet. In the next slide, they finished it for us. And they got the standard deviation of 78.87 by, again, finding the mean, finding the 5 deviations, squaring each of the 5 deviations, adding them all up, dividing by how many we have, or one less than how many we have, and then taking the square root. That is how you find the standard deviation. It's somewhat complicated, but an extremely important measure of spread.
Professor?
Yes.
Where do we divide by 91? That's where I'm kind of.
Whoa, divide by 91. Where do you see divided by 91?
Did you not say
No,
that?
no. If you have 100 data points, you divide by 99.
Oh, okay, never mind. Thank you.
And here we have 5 data points. We divide by 4.
Okay, thank you.
You're welcome. Okay. So let's look at slide 58. Question. The variance S squared, and especially its square root, the standard deviation S, are common measures of variability about the median as center. True A or false B? So hopefully you're all listening a few minutes ago when I said that the median is never used with standard deviation and variance. Those are with the mean, so the answer is in fact B. Very good, everyone got it correct. Let's look at slide 60, which we're not gonna do, we're just gonna, well, I guess we can do it, but it might be too much work. Let's take a look. It says complete the, what's 5:09, what did we get, at 4 o'clock?
Yeah.
Let's take before we look at this question, let's take a 5-minute break. I'm talking too much and my voice hurts, so I'm gonna get something to drink. I need some alcohol. So, I mean, some flavored water. So, we will meet up again in 5 minutes. Thank you, Dad. Very much appreciated. Oh, and people came late. Let's see. Some people said they were here way ago. Let's see. I'm sorry for being late. No problem. No one is actually late. That's okay. And anyone else late? Okay, so I think we're all back. Is there a PDF or worksheet that can be shared with me? So then, you're not in the class. That's right, you're not in the class. Someone trying to add everyone. Yeah, my office hours are in the same zone. So yes, let me just do that quickly. I think I have an email from you, and I can attach it in the email. So hold on. So reply and attach files to the computer and the desktop and chapter 2 PDF. So it is now sent. Okay, so at this point you should have it. And then you can follow along. Okay, so we have on slide 60, we have the following question. It says, complete the calculations for the standard deviation of Mark McGwire's yearly home runs. So let's see what they have there. Home runs by Mark McGwire from 1987 to 1998. In the first column are the years. The years are not our data. The years are just labels. You know, you don't square or use anything with those numbers. The number of home runs, that's the second column. There's a total of how many home runs?
454.
454 home runs. You guys are young. Is any of you old enough to remember when Mark McGwire was actually hitting home runs? Were any of you even born then?
Me,
How old are you?
30.
30. So you were, yeah, so you were a kid. All right, so okay, right? But you were old enough. But probably the majority of you were not even born back in the day. Okay, so we have to calculate X bar. They gave us X, the total. They summed it up for us, 454. And what do we divide by?
11.
I'm sorry, how much?
11.
One more time. I didn't think I got 11.
12.
We divide by 12.
12?
12. Remember, for the mean, you don't divide by n minus 1. For the mean, you divide by n. So you take.
Oh, that's right. Okay.
Right. So you
Sorry,
take,
my bad. I misunderstood.
I forgive you. It's okay. Just don't let it happen again. So you take. That was funny, but nobody's laughing. Okay, fine. So you take your data point, the sum of the data, you divide by 12, and what do you get?
37.83.
37.8333333333, right? 37.83 bar and so on. And then once we have the mean, we go to step 2, which is calculating all the deviations. And if you look at that third column, they did it for us, X minus X bar. They were very nice. They did it for us. And they got it all the values. Notice how some of them are positive, some of them are negative, but what do they add up to?
0.
0, as deviations always do. In the next one, they took the X minus X bar and they squared it. And if you look at all the numbers in that column, you'll notice that they are all positive, which is the whole point of squaring them, so we don't have any cancellation effect. And then we add them all up together, and we get 3757.7. Let's trust their math. The question is, what would be the next 2 steps that I would then take in the goal to calculate the standard deviation? So there's the answer A, I just divide by 12. B, I divide by 12 and then square root. C, I divide by the square root of 12. Or C, I divide by 11 and then square root. A, B, C, or D. We are all muted, so you can't hear our laughs. Okay, I'll believe you. Oh, okay. So B, no, I mean D. Okay, and D, and D, and D, 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 D. So it looks like lots and lots of Ds. And that is correct, right? You divide by n minus 1, 12 data points. So n minus 1 is 11. Then you take the square root. Fantastic. So the next one, okay. So now let's go to slide 62, which says examples of technology. The displays came below from a Textus Instruments Graphing Calculator JMP statistical software in the Microsoft Excel spreadsheet program. Once you know what to look for, you can read output from any technological tool. How nice. Let's look at the first one there, which we're going to learn. If you have a TI like I do, you're going to learn this semester how to use it. But you'll notice that X bar is 31.25. So they give you the mean for this particular example. And they also give you something labeled as SX, 21.8773,495. So X bar is the mean and SX is the standard deviation. They give you both of them. They also give you in the second box, what do they give you in the second box for the same data? What do you notice? They give you the
5-number summary.
5-number summary. So not only do they give you the mean and standard deviation, but they also give you the 5-number summary, including the median, depending on what you want to use. They don't know what you want to use, so they give you both. How nice. The JMP output, you'll notice they also give you the 5-number summary on top. And then they give you the mean and standard deviation on the bottom. And the Excel software, it requires a little more work on your part, but notice how you can program it to give you the mean and what they call the standard error, which is something else, but a little lower is the standard deviation, the median, the mode, the variance, the range, the min, the max, the sum, the count, how many data points, something called the kurtosis, which we're not going to deal with, the skewness. Remember we talked about right skewed and left skewed? Well, there's a mathematical measure of skewness, so you can actually get that. So you get a lot of different data points using technology, and it's all great because who the hell wants to do that by hand? Okay, so let's look on page 63, slide 63 now, about properties of S, properties of the standard deviation. So, property number 1. First of all, we have a name, n-1, which is what you divide by. n-1 is called degrees of freedom. So if I have 5 data points, I say I have 4 degrees of freedom. For reasons that we're not going to get into. It's just called the degrees of freedom. S measures the variability about the mean and should only be used when the mean is chosen as the measure of center. I mentioned this earlier, right? You do not use S with the median. You use S with the mean and only with the mean. The mean, if you recall, was a non-resistant measure. Because S goes with the mean, S is also a non-resistant measure. S is how spread out it is. If you move something far to the right, your spread is going to be significantly larger. So the mean and S are non-resistant measures. S is always greater than or equal to 0 because you're squaring. Do we need a graphing calculator for this class, or would a scientific be okay? I believe this is a class that we're going to use Crunch It. We're going to use a tool online, so you do not need a graphing calculator for this class. But who wants to go through life without a graphing calculator? I know I don't. And I can just... Are you laughing? Are you laughing at what I'm saying? Yeah, you. I see you.
Professor, I took stats and I failed, so I spent like $200 on a calculator. So I
Yeah,
feel like having a calculator is kind of good because it helped a lot, even though I still fail.
That's right. Having a calculator is great. And whether you fail or not, it's something, I mean, just imagine that you're on an island, you crash land on an island somewhere and you didn't have your calculator. What would you do? Right? What would you do? Okay, so make it solar powered, of course, because, batteries run out. But this is important stuff. It could happen. It happened to the people on Lost, the greatest TV show ever. But anyways, moving on. So S is always greater than or equal to 0 because you're adding positive numbers because you're squaring things. When is S 0? S is only 0 if every data point was exactly the same. Okay, if every data point was exactly the same, then the mean would be exactly the same number. The deviations would all be 0. You add zeros, you get 0, you square them or whatever, you square first, then add, you get 0, 0, 0, 0, 0. The only way that S can be 0 is if all the data points are exactly the same. But in general, that's not going to happen, and the standard deviation is going to be positive. Next, as the observations become more variable about their mean, as they get more spread out, S tends to get larger, which makes sense. That's the whole idea. S is a measure of spread. If they're more spread out, you're going to have a larger S. That just is common sense. S has the same units as the original measurements, the original observations. So if you're measuring heights, for example, and you want to know the spread, the standard deviation of heights, if you're measuring heights in inches, then your standard deviation is going to be in inches. If you're measuring something in meters, then your standard deviation is going to be in meters. If you're measuring in seconds, the time, then your deviation will be in time. It has the same units as the observations themselves. And this is one reason why we prefer S to S squared. So this is the last bullet point, because even though S has the same units as what you're measuring, S squared will be the square of those units. So if I'm measuring length in meters, S squared will have square meters as its unit, and that's not the same unit as what I'm measuring, which is why we like S better. So slide number, unless there's a question, slide number 64. When reporting the spread, we prefer the variance over the standard deviation, since the variance is in the same units as our measured data. A, true, or B, false. If you've been paying attention for the last 30 seconds, then you should know the answer to this question. If you get it wrong, I will assume that means that you are not paying attention. And we will have to, oh shit, I'm not gonna do anything anyways. Okay, so everyone got the answer. Everyone who said the answer was B, which is great. It is false. You don't want to use S squared. You want to use S. Or you just looked ahead to the next slide. Either way. Number 66, or slide 66. Which of the following statements is true? A, standard deviation has no units. B, it's either positive or negative. C, it can be inflated by outliers. Or D, it's used even when we do not want to use the mean as the measure of center. A, B, C, or D. So let's go ahead and answer that question. And the answer no. And the answer, everyone got it who answered it. The answer is in fact C. As I just said, it's a non-resistant measure. And mood, Professor, LOL, mood. I don't know what that means, but that's okay. A and B are wrong. That's true. A and B are wrong. And so is D, which is why C is the right answer. So LMAOOO, mood. That's a lot of laughing. Okay, so slide number 68. It means you're reflecting how we all feel. Oh, okay. We're all tired. That's great. All right, but what's your excuse? You're not teaching and taking 9 classes, are you? Are you? No, I don't think so. I hope not. That's crazy. Who would do that? Only a sane person would do that. All right, 6 classes and work full time. Okay, fine, you win. You win. I can't beat that. 6 classes and working full time. Yeah, that's okay. You win on that one. Okay, slide 68. Choosing measures of center and variability. So at this point, we have a choice between 2 descriptions for center and variability. The mean and the standard deviation, or the median and the IQR. So when do you use which? So I already told you this. We did it before we even talked about variability. We use the mean when it's symmetric with no outliers. We use the median when it's not symmetric or there is outliers. As such, the mean and the standard deviation are for roughly symmetric, non-outlier situations, and the median and the IQR are for when there are outliers or it is not symmetric. So the next slide doesn't belong. It makes no sense because it's answering a question that we did a while ago. So let's go down now to slide 70. Question. For the following distribution of Major League Baseball players' salaries in 1992, which measures of center and spread are more appropriate? Mean and standard deviation, or median and the IQR? A or B or C, don't know. Or just write out don't know, because it'll be easier. So looking at the answers, I see lots and lots and lots of one, and I saw at least one person do the other one. So, oh, a few people did the other one. So let's talk about it. Is this distribution symmetric?
No.
Not even close.
No.
It is a very right skew distribution, and we use the median and the IQR for non-symmetric distributions, and therefore the answer is B. We want to use the median and the IQR. Hopefully those who answered A, and there were a few, understand that. I mixed them. Symmetrical would be standard deviation and mean. That is correct. Not just symmetrical, with no outliers. Symmetrical with no outliers. Okay. So finally, 72, slide 72, the question. Suppose you have the following data with a mean and deviation of 5 and 2.1. So they were very nice for us. They already calculated the mean and deviation. If you were to subtract 2 from every observation, what change, if any, would you see in the new mean and deviation? So A, they would both decrease. B, the mean would stay the same, but the deviation would decrease. C, they would both stay the same. Or D, the mean would decrease, but the deviation would stay the same. So try to do this without calculations, because we can always just recalculate if we had to. But we're trying to do this by logic. So A, B, C, or D. Let's take a look at what people have here. So I have 2 different answers. I have an I don't know. That's fantastic. A couple I don't knows. I have a third. I have all 4 answers, A, B, C, and D, and a few I don't knows. So we're fairly across the board on this one. So let's take a look at it. First, what's the average of 1 and 2?
1.5.
1.5. If you lower them to 0 and 1, if you subtract 1 on both and you average those, what's the new average?
0.5.
So the average obviously went down, right?
Yeah.
If you subtract, if all the numbers get smaller, their average is going to get smaller. Okay, does that make sense? Right? If the numbers are smaller, the average of the numbers are smaller, right?
Yes.
So that means that B is out and C is out, leaving 2 possibilities. The mean and deviation would decrease, or the mean would decrease, but the deviation would stay the same. But now let's think about what the deviation is, where it comes from. The deviation comes from deviations from the mean. How far everything is from the mean, we square them, we add them, and so on. If all of the deviations get smaller and the average gets smaller along with them, then the distances from each point to the average would not change, because all you're doing is you're taking your data and moving it to a different spot on the number line. But the spread, how far out apart they are, is exactly the same size. So because the spread is exactly the same size, the deviations will all be the same, and therefore the deviation, the standard deviation will be the same. So the answer would be D. The mean would decrease, but the standard deviation would stay the same. Okay, not the most obvious answer, requires a little bit of thought. But this does take us to the end of PowerPoint number 2, chapter 2, 2 weeks. That's a great rate. I think it's fantastic. I think it's time to have a quiz sometime. Practice quiz. You have practice quiz online with your homework and Sapling, and it's time to have an actual quiz, I think. Otherwise, I get fired for not following the rules. We don't want that, do we? No one's answering.
sir.
Great. No, that's good. Thank you. Shall we expect to see this in a further quiz/test? Well, everything we learn, you should expect to see on a test or a quiz, right? That's what quizzes are. They're open note quiz. Sure, why not? Okay. Open note quizzes are fine. Not, shut up. Not open professor quizzes or open friend quizzes or open Google quizzes, but open note quizzes are fine. Okay. Reminds me of a story someone told me once that his teacher said, I'm giving you guys a test next week. Anything that you can carry into the class with you, you can use. So someone brings in a stack of textbooks. Someone brings in their computer. This is back in the day before we had, handheld things. And someone literally, so the story goes, carries a person with them into the room who was a professor in that course. So he carried the professor in. I don't know if it's a true story or not, but I'm too heavy. No one's going to carry me. So it is what it is. Open parents, no, unless your parents don't know anything, then you can use them. But if your parents know this stuff, then no, open parents is out. So no open parents. I play rugby. Congratulations. I will inform the media. We'll have a big parade and everything. Oh, I think I can carry. All right. Well, I weigh 280 pounds. I know I don't look it. I look nothing more than 278, but I do. And if you can carry me, challenge accepted, someone said. I love it. I love the confidence. Fantastic. Always take a challenge. Anywho, that neither being here nor there. This is the end of the fourth.
I do have a question real quick.
160 in
Bob.
I don't know what that means. Your eyes weigh 160? Oh, you're saying, oh, thank you. You're saying you see me as being, oh, that's the sweetest thing anyone's ever said to me. Thanks so much. For how many yards can he carry you? It's a she. A she says, I play rugby and she can carry me. So that's very sexist to think it was a he. That's horrible. But I have no idea. Maybe she can respond. How many yards do you think you can carry me? She who plays rugby.
I would say at least 20 yards.
20 yards, 60 feet. Wow. That's a statement right there. In your dreams. I can lift you in my dreams. Thank you. You lift me just by being in my class. So I feel that we're syncing here.
I do have a question from the homework though.
Go ahead.
Part of the homework asks us about which graphs we would use in certain situations, and
Yeah.
I didn't quite understand that concept.
Which graphs would you use in certain situations? I don't know what the question was. If you want to
Is that the one that was asking for pie chart or stem plot?
Yeah, between pie charts, stem graph, and box.
Oh, so that would be basically the categorical or quantitative, right? We use different graphs for categorical variables versus quantitative variables. So my guess is I don't know all the questions by heart, but my guess is that's what the question was about. Is that what it was? He who just responded and helped?
Is it from chapter 1, the homework from chapter 1?
I don't know. It's her question.
Yes.
Yeah, that one, there's two options that have both selections.
You mean there's a mistake in the homework program? Is that what you're saying?
Not necessarily, just kind of how it's worded.
Well, I don't want to keep everyone because it is 5:40. If you want to stay after for my office hours, I'm more than happy to load it up and to take a look at it. But if people want to go, I don't want to keep you guys because class is over. So have a great Labor Day weekend. Do a lot of math because that's the only way to truly celebrate a holiday with lots and lots of math, and that's what I do. So I will see you all next week and be ready for a quiz next week. And this homework is due a week from today. So we finished chapter 2. So the chapter 2 homework is due next Thursday. So have a great week, everyone, and go away. Have a good weekend. Thank you. You too. I will. I'll try. I promise. I'll do my best. You're welcome. Thank you. You too. Blessed weekend as well. Power, all good. You're welcome. You're welcome. I'm going to stop recording now before